The title of this presentation is Poisson Structures, Quantum Inverse Scattering, and Integrability for the 11 vertex model. To begin with the presentation overview, we'll be describing and motivating connections between the 4 vertex, 6 vertex, 11 vertex, and 20 vertex models. And in doing so, to describe such connections from previous works of the author and myself, we're going to formulate transfer matrices, quantum monodromy matrices, as well as product expansions of L operators. And in doing so, our work is fundamentally going to rely upon seminal work of Fadeev and Takhachan, which I'm going to be describing for the viewer, which we will spend the first few slides of the series recounting briefly a few aspects of this work. And after this brief overview of a few aspects of their work, we're going to describe how action angle variables or action angle coordinates and related quantities can be used to study a wide variety of vertex models in statistical physics. And just to begin, this is a reference that I'm going to be describing how basically one can be able to use and leverage certain aspects of this work just basically to study integrability and exact solvability of different models in statistical physics. And this is of great importance, this work, because pretty much the fact that a lot of this work, as I'll be describing, is relating to well-posedness of solutions either to the nonlinear Schrodinger's equations or other partial differential equations which are underlying wave propagation, or alternatively also quantum phenomena, which is encompassing a wave particle duality, is very important because it's pretty much being able to give us the opportunity to leverage and to make use of this framework for a wide variety of models with different types of boundary conditions, which can exhibit different types of asymptotic behaviors as we're taking the support of a domain, as we'll be describing throughout various quantities that we'll be introducing, to exhaust an entire lattice, whether it either be the square lattice in 2 dimensions or the triangular lattice in 3 dimensions, and how pretty much vertex models in either 2 or 3 dimensions can be studied with this framework. And this is pretty much the overall thrust of this seminal work, this Springer-Verlag publication in Classics in Mathematics, in which pretty much these two authors are describing Hamiltonian methods and the theory of solitons. And solitons are pretty much coming up from the fact that, as I'll be describing for the viewer, there are just basically solutions to the KdV equation, the Korteweg-de Vries equation, which are very much relating to wave propagation and phenomena, and how this establishes a lot of comparisons with solutions to the nonlinear Schrodinger's equation, which I'm also going to begin further describing for the viewer. And so first, I wanted to start out directly from their work again, a solution or a statement of the NLS equation, the nonlinear Schrodinger's equation. And in particular, this is different from the typical Schrodinger's equation due to the fact that we have the presence of a nonlinearity, this term 2 kappa times the absolute value, or the magnitude of the absolute value squared of the wave function, which is the solution to this nonlinear partial differential equation, times the wave function itself, psi. And this nonlinearity term is very important because depending upon the magnitude of kappa, which is the multiplicative prefactor, which is coming into play in the statement of this nonlinear partial differential equation, that's being multiplied by the magnitude squared of the wave function times the wave function itself, can have a wide variety of physical significance. For instance, if you take kappa to be strictly positive, we can describe solutions to the focusing nonlinear Schrodinger's equation. And otherwise, if you take kappa to be strictly negative, you can describe solutions to the defocusing nonlinear Schrodinger's equation. And this equation is very important because the solution which we're talking about, psi, is very important to study in terms of making connections with Sobolev space and regularity for determining whether there are any types of conditions or well-posed initial data in which we'll be able to obtain, maybe in some type of nice closed analytical formulation or involving exponential functions, which can be used to describe basically behaviors of ensembles of particles, and basically which is underlying the Heisenberg uncertainty principle, which is just pretty much stating that counterintuitively non-locality of the universe is relating to the fact that if we look at close to atomic scales, we're not able to measure the momentum and the position of particles with infinite precision simultaneously. But besides the nonlinear Schrodinger's equation that I just provided in the previous slide, and in the physical significance of that nonlinearity, which is coming into play with that kappa term, we also have the KdV equation, the Korteweg-de Vries equation, which is another partial differential equation of interest because it can pretty much be analyzed and studied through the existence of suitable action angle coordinates, which I'm going to provide a few explicit expressions of from this seminal work in mathematics due to Takhatan and Faddeev, and how this actually relates to integrability and exact solvability. And in this case, in comparison to the solution state or the solution of the nonlinear Schrodinger's equation, which was given in the previous slide, which is dependent upon the wave function psi, the solution of the KdV equation is typically denoted with u, little u. So it's just basically saying that this is another nonlinear partial differential equation of interest, given the fact that instead of having a second order derivative, which is appearing in the statement of the previous slide as we see through the nonlinear Schrodinger's equation, we're instead having a third order partial derivative of the solution. And instead, in a similar way that the nonlinear term in the nonlinear Schrodinger's equation is dependent upon some magnitude of the solution state wave function psi, this term corresponding to a nonlinearity of the KdV equation is also dependent upon 6u, namely the solution, some prefactor, some constant prefactor times the solution itself times the first partial derivative of the solution. And okay, so besides the fact that we've been motivating and describing how the nonlinear Schrodinger's equation and the KdV equations, which respectively underlie quantum phenomena and wave propagation phenomena, can be used within this framework, we have to actually describe the Poisson brackets. And the Poisson brackets within quantum inverse scattering methods come into play because basically you're looking to formulate L matrices or products of L operators, which you're looking to be able to determine whether there's some favorable or some type of beneficial or amenable asymptotic representation of these operators over finite volume, namely over the whole lattice, which for a case of two and three-dimensional vertex models is either the square lattice or the triangular lattice, respectively, and basically then being able to make use of these operators for computations with the Poisson bracket. And like I've been describing, is that what's really powerful about this seminal framework due to Faddeev and Takhatan is that you can pretty much make use of these types of computations given a wide variety of L operators, which I'm going to describe and consolidate for the viewer in this presentation, in this single presentation. And pretty much the fact that for the nonlinear Schrodinger's equation, we're going to note psi of x and bar psi of y as respectively as the action angle coordinates and the complex conjugate of the action angle coordinates at the points x and y within some finite volume, which is identically being equal to I times the delta function of x minus y. So this delta function is identically equal to 1 if x is equal to y, and otherwise it's equal to 0. So pretty much it has mass 1, pretty much identically equal to 1 if x and y are the same point, but otherwise if x and y are two distinct points within the support of this finite volume, this delta function collapses to have mass 0. And the Poisson brackets for the KdV equation take a very similar form. Namely, the fact is that if we also look at denoting some action angle coordinates u of x and u of y, we're looking at the Poisson bracket of these two terms at, again, two distinct points x and y. It's given by the fact that we're still having this delta function, which is giving a mass if x and y are the same point or are identically the same point, or 0 otherwise. But we also have a different type of prefactor, namely, if you look at the action angle coordinates in the previous slide, we have this I factor because I is emerging as a prefactor in terms of the time evolution that we're performing on the solution state wave function for the nonlinear Schrodinger's equation. But otherwise, we're having a 1/2 term multiplied by the partial derivative in y minus the partial derivative in x. And initial data, like we've been describing, is very important when we're describing either solutions to the nonlinear Schrodinger's equation or to the KdV equations, and pretty much any type of partial differential equation of interest. Is really relating to the fact that when we're looking to either perform time evolution to determine whether there's some type of well-posed class of initial data in which maybe a rough approximation to an analytical solution could exist, or in which there could be some type of solution approximation at all, pretty much we have to restrict at the beginning of the time evolution when t is identically equal to 0, the behavior of the solution so that we can enforce some initial condition in the case of which in the case of the nonlinear Schrodinger's equation is proportional to the following quantity, namely the solution state wave function psi, which is a function of x and t when we're first beginning the time evolution to determine whether there's some initials, whether there's some uh, you know, whether there's some analytical formulation to the solution is pretty much identically equal to psi of x, namely the fact that at the beginning of the time evolution, when we're forcing initial conditions, there is no dependence of the solution state wave function to the nonlinear Schrodinger's equation on time. But also, we have to keep into mind when we're looking at well-posed initial data in different types of ways, which we can pretty much be able to solve some type of partial differential equation of interest, either analytically or maybe with some type of numerical methods or numerical simulations, is the asymptotic behavior of the solution. And in the case of the nonlinear Schrodinger's equation, this seminal work and reference that we've been talking about for the Hamiltonian methods in the theory of solitons, they're describing the fact that the solution state wave function to the nonlinear Schrodinger's equation psi of x of t as x tends to plus or minus infinity, namely as we let the point or the support of the finite volume either approach negative infinity or approach positive infinity, is given by some rho per factor, namely some density per factor, times exponential of I, phi plus of minus of t, where this phi plus or minus of t term, which is dependent upon whether x tends to negative infinity or a positive infinity, respectively, is only dependent upon time, and whether there's some in this particular case, there's a very nice type of analytical expression which is able to encapsulate how the asymptotic behavior of this phi plus or minus of t terms relates to the asymptotic behavior of psi x of t. And the explicit definition that's given in this work in terms of the Poisson bracket is basically given involving two test functions. So basically, we're fixing big F and big G as two test functions. And in particular, for computations with the Poisson bracket, which are being performed from solution state wave functions of the nonlinear Schrodinger's equation, we're looking at some per factor I multiplied by the integral over the whole real line, namely over from negative infinity to positive infinity, of just basically the difference of these two expressions against the standard Lebesgue measure. Just basically the fact that we're looking at the derivative of the first test function with respect to the solution of the nonlinear Schrodinger's equation multiplied by the partial derivative of the second test function g, which is again taken with respect to, instead of just the regular nonlinear Schrodinger's equation, just basically the complex conjugate, as well as for the remaining term, subtracting the product of two remaining partial derivatives, namely the first term, which is the partial derivative of the first test function with respect to the complex conjugate of the wave function solution for the nonlinear Schrodinger's equation, and finally the partial derivative of the second test function g with respect to the partial derivative of the solution state wave function of the nonlinear Schrodinger's equation. So pretty much in some type of way, really the Poisson bracket that is being used to make some type of conclusion about action angle coordinates, whether it be for the nonlinear Schrodinger's equations or for the KdV equations, is really relating to the fact that we're looking at some integral over the entire real line, which is again representing the phase space over which we would like to determine some type of solution for this nonlinear partial differential equation under well-posed initial data. And pretty much we're looking at some type of anti-commutation relation with respect to this integral, and hence with respect to the Poisson bracket, because we're pretty much interchanging the order in which we're taking the partial derivative of these two test functions. Namely, either we're looking at the partial derivative of big F or big G with respect to psi of x or the complex conjugate of psi of x, or alternatively, for the remaining term, we're looking at the product of the two partial derivatives of the first test function with respect to the complex conjugate, instead of just the bar of psi of x, instead of just with respect to psi of x, and also with respect to g and psi of x. And the whole point that we've been describing in terms of L operators and how this relates to expressions that we're going to be describing with regards to the transfer in the quantum monodromy matrices is really given by the fact that we would like for there to be some vanishing of the Poisson bracket with respect to action angle coordinates. And obviously, the physical significance of this is that when there's a vanishing of the Poisson bracket, you're able to make some type of conclusion that the dynamics of the system of interest is roughly linear because pretty much the vanishing of this Poisson bracket is saying that this type of analytical expression, which we gave in the previous solution or the previous expression from the Poisson bracket in the slide before this one, is that it's pretty much approximately zero, which is indicating that there are no higher order terms of the dynamics for the system that we would like to consider. And this is given by the fact that in the first equality, for the action angle coordinates that one can construct or hope to construct with respect to the nonlinear Schrodinger's equation, psi of x and psi of y is identically equal to the complex conjugate of psi of x with the complex conjugate of psi of y, which vanish, as well as given by the fact that if we don't take both of the arguments to be either psi and a psi or complex conjugate of psi with a complex conjugate of psi, what we're going to be able to obtain for the Poisson bracket is psi of x with the complex conjugate of psi y is equal to I times the delta function, namely the delta mass that I described for the action angle coordinates for the KdV in the nonlinear Schrodinger's equation in a previous slide. And it really shouldn't come as a surprise that the polybasis elements are really underlying a lot of these types of computations that we're looking to perform with the Poisson bracket and how this is still really demonstrating how quantum mechanics and quantum information theory, like I've been describing in some of my other presentations on my YouTube channel this year, is really kind of lurking in the background, and it's a primary physical motivation for all these types of conclusions that we would like to hope to glean and to make with respect to action angle coordinates. And obviously, this is again relating to the fact that the universe is locally not real, namely the fact that we're having this Heisenberg uncertainty phenomena, which is relating to the fact that we're looking at these polybasis elements, which is the following collection of tracelets, namely trace zero, 2x2 matrices, namely sigma 1, which is just ones along the antidiagonal, sigma 2, which is a -1 and a 1 along the antidiagonal, sigma 3, which is a 1 and a -1 along the main diagonal, and also sigma plus and sigma minus, which can be taken in terms of linear combinations of either sigma 1 and sigma 2, or sigma 1 plus sigma 2, or sigma 1 minus I sigma 2. And the finite dimensional representation of the transfer matrix is given by the following expression, namely that we're looking at the transfer matrix, which is taken as a function of lambda. And lambda is typically taken in several types of computations throughout the literature to also be equal to u, which is a spectral parameter. And a spectral parameter is used along is a very important object that's introduced for vertex models in 2 and 3 dimensions alike, because pretty much you're looking at whether you can introduce any types of staggering for a vertex model in 2 or 3 dimensions along the rows or the columns or any degrees of freedom from the underlying lattice. And this would pretty much allow one to determine whether there's some type of defect in a material. And of course, these types of defects can be of interest for percolation models or other types of phenomena, even for more applied areas like material science, in which you would like to see maybe if there's some type of superconductivity property or other types of favorable properties that basically a material can still exhibit, maybe when you're going to very low or to very high temperatures. And this is given by the fact that the first column of this finite dimensional representation for the transfer matrix is given by A of lambda and B of lambda, whereas the second column is given by epsilon times the complex conjugate of B of lambda, and as well as the remaining entry for the second column is given by the complex conjugate of A of lambda, where this epsilon factor, which is appearing in terms of the first entry of the second representation of this finite dimensional representation for the transfer matrix, is given by the sign of kappa, where kappa, recall, is the magnitude of the prefactor for the nonlinearity, which we had given for the nonlinear Schrodinger's equation. And pretty much how this protector can have the physical significance is that if it's strictly positive, it corresponds to a focusing solution of the non to a solution of the focusing nonlinear Schrodinger's equation. Whereas if it's strictly negative, it corresponds to a defocusing to a solution of the defocusing nonlinear Schrodinger's equation. And so now I'm going to be further describing how a lot of these ideas and these types of main, takeaways or ideas between mathematical physics, integrability and exact solvability, statistical physics and quantum physics, many areas of research that I'm very interested in can be described in terms of a specific problem from a few groups of authors and how this relates to several preprints on the archive that I've been having over the past year or two. And this is pretty much saying that besides the dependence of the six vertex model on either flat and slope boundary conditions, which are two different types of classes of boundary conditions that one can introduce for having defects in some type of model of statistical physics, there are more algebraically focused characteristics of the six vertex model presented in a previous video from a presentation of a series on my YouTube channel which enables us to study the six vertex model and to examine it from more of an exactly solvable and integrable perspective. And this is pretty much given by the fact that in another presentation on my series, when I was talking about the six vertex model and the 20 vertex model, and even Yang-Baxter algebras and how this relates to R matrices, which I'm going to be introducing later in this presentation in the series, one can look in terms of making use of and leveraging um, a lot of the contributions and seminal fundamental contributions and seminal work in this book from this Springer-Verlag publication from the Hamiltonian methods and the theories of solitons towards actually being able to deduce that integrability of a Hamiltonian flow for the inhomogeneous six vertex model holds from integrability of limit shapes. And it's pretty much demonstrating how all of these types of aspects of integrability and exact solvability can be studied for a wide variety of vertex models under many types of different boundary conditions. However, in particular, though, it's really helpful to actually think about very carefully what types of boundary conditions, which are kind of relating to the types of initial data and initial conditions of solutions for either the KdV or the nonlinear Schrodinger's equation that we were talking about through the statement of the two partial differential equations, which I had presented at the very beginning of this presentation. And so basically, we're trying to think to ourselves, how can the work from Keating, Reshetikhin, and Sridhar from their project, from their paper, from their publication in Communications in Mathematical Physics on integrability of limit shapes for the six vertex model in the presence of inhomogeneities basically be leveraged and described to deduce that some integrability of a Hamiltonian flow can be concluded, and how this relates to action angle coordinates and well-posed initial data and other types of related characteristics for Hamiltonian methods in the theory of solitons that was given in this fundamental work that we've been describing for a little bit of time now in terms of basically the connections between several areas of mathematical physics and probability theory. And this is to say that these two references are related to the fact in that they both commonly define some type of Hamiltonian flow, and they show that integrability conditions can be shown to hold from computations with the Poisson bracket from entries of the transfer matrices, which is eventually, like I mentioned, relating to determining how some type of finite dimensional representation of the transfer matrix would be related to some type of infinite dimensional representation. However, it leaves open the possibilities for applying the QISM type approaches, namely the quantum inverse scattering method type approaches for other types of settings. And that's really what I'm going to be describing more throughout the remainder of this series, namely what would be the types of objects that would be helpful and how they would relate to the 11 vertex model, because the 11 vertex model, it's a bit more of an esoteric model of statistical physics, and it has connections and physical motivations more relating to polymers, which are kind of different from connections of the six vertex model with the O'Connell-Ure polymer. And the O'Connell-Ure polymer is just a very well-known polymer that has various types of connections to KPZ universality, as well as to other types of maybe conjectured universality classes, which can be related to and deduced from solutions to the KPZ equation, which is basically a nonlinear partial differential equation that was motivated and described a long time ago uh, the three groups of physicists, Carter, Parisian, Zhang, and Zheng, for just basically being able to describe basically universality classes of percolation types processes, as well as several other objects that are of interest to statistical physicists. And there are several other references for discussion conditions for integrability and exact solvability that I didn't mention necessarily in previous talks of this series that I felt would be good to continue motivating before we're getting into the 4 vertex model, the 6 vertex model, the 20 vertex model, as well as how these 3 vertex models can have connections with the 11 vertex model. And this is just basically to say that in another related work, the beta ansatz and the inverse scattering method transform were described for a box ball system. And a box ball system, it's another type of model in statistical physics that I'm not really going to be describing or going into as much in this presentation on the series, but there are a lot of very interesting research talks given at UCLA and other places that I've even seen in person that were describing basically integrability of these types of systems and how is underlying connections to the beta ansatz, which I'm going to be describing. And as well, in another solo publication by Just Fadiv, he talked about how algebraic characteristics of the beta ansatz work for an integrable model. So basically touching on some other types of connections, which I'm going to be discussing for the viewer, in which Fadiv looked at just basically how the beta ansatz and solutions to the Yang-Baxter equations, which I'll be describing, can be used and related to integrability and exact solvability. And even in a third reference by Kuniba and Tagaki, they describe how there are connections between the beta ansatz, the inverse scattering transform, and also the Riemann theta functions for just basically automaton. And automaton are just basically another type of model in statistical physics which have connections to various universality classes and potentially also to KPZ universality. And finally, a final reference that's given on the slide by Skylanen is also talking about the quantum inverse scattering method. So this is just to say that the quantum inverse scattering method, since this seminal work of Faddeev and Takatan, which is relating to the nonlinear Schrodinger's equation and the KdV equations, as well as well-posed initial data and boundary conditions for these types of partial differential equations of interest, is something that has really attracted a lot of attention relating to these topics from these few selected references in the literature. And now I'm going to describe basically how the D2-3 spin chain, which is a connection to a higher rank spin chain in statistical physics, can be used to describe inhomogeneities in the 6 vertex model. So this is just basically given by the fact that I described for the viewer in previous slides of the presentation how basically the Yang-Baxter equation and the beta ansatz can be used to describe or to motivate some types of connections with integrability and exact solvability, as well as the intricate dependency of these boundary conditions on just basically exact solvability and integrability. And now I'm just going to basically be describing some of the types of connections with the 6 vertex model in spin chains and how this can be used to accommodate inhomogeneities through staggering of spectral parameters. And this is just basically given by the fact that the R matrix will be shown to be related to finding solutions of the YBE, the Yang-Baxter equation, just basically given by the fact that this R matrix for the 6 vertex model in the presence of inhomogeneities is given by identically being equal to being a function of the spectral parameter U, as well as a function of H and V, two external fields, which, according to, as it shouldn't be a surprise for physicists, it can be taken as the electric field and the magnetic field. And in the presence of these two external fields, the entries of the R matrix are given in terms of this following finite dimensional representation, namely given by the fact that we're having terms along the diagonal which are given by either being proportional to the exponential of h plus v, the exponential of h minus v, the exponential of minus h plus v, or the exponential of minus h minus v, as well as two terms along the antidiagonal, which are proportionally given to C. And A, B, and C are given in terms of the six vertex model that appear throughout several works in the literature as the isotropic parameters, which are given in terms of the six vertex model. And this really shouldn't come as a surprise because these isotropic parameters and these isotropic weights, which are used to define the six vertex model, which appear directly from the entries of the R matrix for the six vertex model in the presence of inhomogeneities, is really given by the fact that it's related to just basically collapsing the weights for every pair of two configurations being equal to each other. Namely, the fact that the sample space of the six vertex model has six possible configurations from hence the name from just basically configurations which satisfy the ICE rule. You can just basically groups of two parameter or two configurations. So just basically set the first two configurations weight equal to A, the second two equal to B, and the last two equal to C, and how this can be used to populate entries of this finite dimensional representation for the R matrix. And altogether, like we've been describing, is that if we take minors, namely little chunks or restricted chunks of this finite dimensional representation for the R matrix, we can be able to study solutions of the Yang-Baxter equation by looking at just R of 1, 2 of U minus V, just taking just basically one spectral parameter U minus another spectral parameter V being multiplied by R1 of 3, which is just a function of U, and R2 of 3, which is just a function of V, and just basically being able to perform a type of intertwining relation from the product of these R matrices on the right-hand side of the Yang-Baxter equation, which is given by R2 of 3 of V, R1 of 3 of U, as well as R1 of 2 of U minus V. And this Yang-Baxter equation, which is pretty much relating to a very general type of relationship, which is of great interest for mathematical physicists and statistical physicists to study, is because it pretty much allows us to determine what type of integrability or exact solvability structures can we basically be able to conclude and to deduce from the R matrix, which is proportional to the weights, which are also a function of, again, the spectral parameters in the two external fields, as well as with respect to the isotropic parameters. And this is overall relating to just basically the D23 spin chain because it's a quantum spin chain of interest from one of my previous preprints on the archive that I'm going to be updating with another version soon, because it pretty much relates inherently to a lot of computations that one can hope to perform with the Jimbo R matrix. And the Jimbo R matrix is a different type of R matrix that's given from just basically this very simple finite dimensional representation of the R matrix for the six vertex model in the presence of inhomogeneities from the previous slide. And it's basically given by the fact that the Jimbo R matrix is expressed in terms of summations of tensor products of elementary matrices. And it's quite a handful because there are a lot of different types of components which come into play in terms of the Jimbo R matrix. But altogether, this can be used to define the transfer matrix of the D23 spin chain, which as a higher rank spin chain, the transfer matrix is proportional to the partial trace of this product of terms, namely a product of K matrices under open boundary conditions, as well as a product of R matrices, as well as two other remaining terms for just basically the K matrices and R matrices for other superscripts. So basically where this plus and minus superscripts can determine and pretty much indicate how boundary conditions are enforced over a finite volume for this higher rank spin chain that I'm just very briefly drawing the attention of the viewer to. But to further study other properties of such L operators, we introduce a change in notation for studying the large N limit, namely the large asymptotic limit of the three-dimensional transfer matrix. And a three-dimensional transfer matrix can come into play because it's very much related to what we have been talking about and motivating in terms of basically the transfer matrix for the six vertex model, because one could hope basically to be able to study transfer matrices for the six vertex model and then to be able to deduce maybe some type of integrable or exactly solvable structure for the 20 vertex model, which is a higher dimensional analog of the six vertex model. But fortunately from us, as I've described in previous presentations of my series on this channel, we can make use of domain wall boundary conditions that are basically encoded in three dimensions for the 20 vertex model due to Di Francesco. And DiFrancesco, in a lot of his seminal work, he really discusses and motivates determinantal representations for partition functions of the 20 vertex model, and pretty much how this can be used to establish connections from determinantal representations of the partition function for the 6 vertex model under domain wall boundary conditions. And pretty much the fact that you have encodings of domain wall boundary conditions for the 6 vertex model and also for the 20 vertex model, it kind of establishes more of a clear link in terms of integrable and exactly solvable structures that one would hope to be able to deduce or be able to conclude of from this model. But the Poisson structure, which is another title and another keyword which is introduced in the title of this presentation and how it relates to the 11 vertex model, can be deduced from the fact that we're looking at the following family or collection of Poisson brackets, namely A of U with A of U prime, and so on all the way up to D of U and D of U prime for these, for these 16 Poisson brackets, which are used together, which is overall drawing your attention to the fact that in 2 dimensions, the number of Poisson brackets that must be approximated depends only upon the 4 entries, namely the 4 operator representations in finite and infinite dimensional representations of the transfer matrix A, B, C, and D, which are appearing in the expression obtained for the transfer matrix by multiplying L operators together. So that's pretty much how the action angle coordinates and well-posed initial data for partial differential equations and how quantum information theory and quantum mechanics can be related to exact solvability and integrability, because we're basically taking an L operator, making sure that there are some just favorable boundary conditions that are enforced for this L operator, and being able to perform computations with operators from the Poisson bracket, which are relating ultimately to terms which are appearing in L operators. And this is to say that the expansion of the 2-dimensional transfer matrix, say, for the 6-vertex model in the presence of inhomogeneities, as well as the 4-vertex model and closely related models, can be related to the large N asymptotic limit from the products of L operators, just basically looking at a product of 0 between little I, between big N, of 1 of I, 2 of I, 3 of I, and 4 of I, where each one of these terms is going to inform the types of operators that we're going to be trying to asymptotically approximate from computations with the Poisson bracket. And I also included this other type of finite dimensional representation because it's representing one type of very complicated representation from a work that I had for the 20 vertex model under domain boundary conditions, in which pretty much due to an oscillatory algebra as well as root systems, another reference which I described in another presentation in another series on the channel titled Exercises with the Universal R Matrix due to Booz and colleagues, they basically describe how you can construct some type of operator from just basically a tensor product of quantum groups, and how this relates to constructions of the universal R matrix, which is another very type of intricate R matrix. So it really shouldn't come as a surprise to the viewer that there are several types of R matrices, whether you're looking at, again, the R matrix in the presence of inhomogeneities, the universal R matrix, or other types of R matrices, which would then be able to, which could be leveraged for computations with the Poisson bracket and with action angle coordinates to determine whether some type of integrable or exactly solvable structure holds. In the expansion of the 2-dimensional transfer matrix and the large N asymptotic limit from the product of L operators in the presence of the 6-vertex model with inhomogeneities, it can be expressed in terms of products of these type of forms. So just basically, I'm not explicitly defining all these expressions because these computations are very intricate, but they're just basically relating in terms of some function of the spectral parameters lambda of alpha, as well as some sign of 2 eta term where eta is some strictly positive parameter, as well as I, which again should not come as a surprise, is just basically the index of this term, which is appearing in this asymptotic approximation for finite dimensional representations of the transfer matrix, and how basically you can make use of computations for one operator to determine and to deduce some type of finite dimensional representation for all of the 3 remaining operators in this representation for the transfer matrix. And so we can define the triangular ice model, which again I've been describing by making use of some observations and work from DiFrancesco is relating to the fact that we have to define some type of series of weights which are introduced for this model, which in the case for the 20 vertex model is given by the following series of expressions. Basically, we're defining W naught, W1, all the way up to W6, namely six weights, which are given by various products of these terms, which are relating to the isotropic parameters, which I described for the viewer early in the presentation of the series, through the definition of the R matrix for the inhomogeneous six-vertex model, and how pretty much as a generalization in three dimensions of the ice rule, it's given by the fact that you either have to have zero arrows pointing inwards or three arrows pointing outwards, as well as which is given respectively by these omega naught terms or W naught terms, just basically the configurations within the sample space of the 20 vertex model, which have a weight of W naught, which is pretty much given by either having all of the arrows pointing outwards from this samples from this configuration and the sample space provided in DiFrancesco's picture, as well as either all of the arrows pointing inwards, as well as pretty much all types of different, basically different types of configurations of the arrows that are pointing inwards or outwards amongst every one of the vertices which are given in the triangular lattice. And we can also furthermore be able to depict different types of ways in which these types of configurations, which are colored using lines in the previous slide of the presentation, can be related to just basically configurations which are described in terms of arrows or establishing some type of directionality, which is an equivalent way to define configurations within the sample space of the 20 vertex model that is often used throughout the literature. And if we look at the first left-hand most side where my cursor is right now of the sample space of the 20 vertex model, we can see just basically that these types of configurations all have arrows again that are pointing outwards. Namely, we can see this first direction of freedom that I'm pointing my cursor along for the triangular lattice is pointing away from the vertex, as well as the two remaining directions or arrows along the two remaining edges of the triangular lattice are also pointing outwards, whereas basically there's an opposing or opposite directionality of these arrows in the configuration which appears right below it, namely the fact that we're reversing the orientation of all the arrows among each one of the 3 degrees of freedom for every vertex in the triangular lattice. And just basically using these local rules, namely these rules that are used to sign configurations about every one of the vertices of the triangular lattice, that we can use these types of rules to define just basically configurations supported over a finite volume and even over a weak finite volume limit over the triangular lattice for introducing a probability measure for the 20 vertex model, which can be used from the types of weights which I introduced in the previous slide. But altogether, we're discussing and motivating quantum spin chains in the 6 vertex model and the 20 vertex model, and what's coming up even the 4 vertex model and the 11 vertex model, to further describe where additional computations with the Poisson bracket arise, in which for the 20 vertex model, given the universal R matrix and the universal Yang-Baxter equation, we can look to define some three-dimensional representation of the transfer matrix, which is given by the limit as big N tends to positive infinity and big N tends to positive infinity of this boldface T, which is corresponding to the transfer matrix, as well as the trace of this boldface T, which is corresponding to the asymptotic representation of the quantum monodromy matrix, and how, again, this is really drawing our attention to the Poisson structure for the 6 vertex model in the presence of inhomogeneities. And so from the large three-dimensional large N limit, the entries of the transfer matrix when forming the system of Poisson brackets of entries of the transfer matrix take the following form. Namely, if we're looking at infinite or asymptotic representations in the large N limit for the transfer matrix and the trace of the transfer matrix, namely the trace of the quantum monodromy matrices, is just basically amounting to looking at whether the types of behavior of the operators A, B, C, D, E, F, and G, H, I, which are appearing in the 3 columns for the representation of the transfer matrix, and how ultimately this is relating to some computations that one would hope to perform with the Poisson bracket. And for the instance of this Poisson structure, there are more brackets that are considered. However, from the fact that we can see from some of the brackets which are included in the Poisson structure, namely C of U and A of U prime, namely U and U prime being two spectral parameters over the triangular lattice, are used to just basically relate these Poisson brackets to the Poisson brackets of action angle coordinates and hence to integrability and exact solvability. But more generally, for all entries of the three-dimensional transfer matrix, components of the set of 81 relations can be formed by making generalizations from two dimensions, namely, again, the fact that we're having this three-dimensional representation for the transfer matrix, namely the finite and weak and infinite dimensional representations from these three columns of the transfer matrix is just basically given by the fact that we're looking at a family of Poisson brackets, hence a higher dimensional analog of the Poisson structure, which is just basically relating to looking at either, as we can see from Poisson brackets 1 through 9, being A of U with A of U prime all the way up to I of U prime, as well as for Poisson brackets 10 through 18, B of U from B of U with A of U prime all the way up to I of U prime, and so on and so forth, namely C of U up to with A of U prime all the way up to I of U prime. So it's just pretty much resulting in the fact that we have to consider more types of combinatorial possibilities for these Poisson brackets, depending upon the operators which are given from the transfer and quantum monodromy matrices. And in three dimensions of analog of the tensor product of Poisson brackets of the entries of the Largent transfer matrix takes the following form, which is just basically relating to the fact that in a previous representation for the Poisson bracket, I described just basically a Poisson bracket with respect to standard multiplication of real numbers as basically the term which is appearing between partial derivatives of the test functions with respect to either the solution to the nonlinear Schrodinger's equation or with respect to the complex conjugate of solutions to the nonlinear Schrodinger's equation. But one can also look in terms of the tensor product of the Poisson bracket, namely replacing ordinary multiplication with a tensor product and how this actually relates to just basically as we show in the first line in the first equation on this slide, namely the transfer matrix T minus as just basically one of the parameters tends to minus infinity or to positive infinity of just basically T minus of x of lambda with the tensor product with respect to the Poisson bracket of T minus x of mu, namely the same spatial point with respect to a different spectral parameter u, where lambda and mu are spectral parameters that are not equal to each other, which is, again, bringing forth another type of manifestation and expression of this type of anti-commutation relation in which we're looking at a perfactor r of which is a three-dimensional function of lambda minus u times the tensor product of T minus of x of lambda with T minus of x of mu, or minus the tensor product of T minus x of lambda tensor product with T minus x of mu, multiplied by r to the three-dimensional function of r times lambda minus mu. And it shouldn't come as a surprise at all that instead of considering some type of asymptotic representation as x or as the spatial parameter tends to minus infinity of this Poisson bracket of the tensor product of these two transfer matrices, that one can basically also look at T plus of x of lambda of the tensor product with respect to the Poisson bracket of T plus of x of mu, and how this takes forth a very similar type of expression, namely the fact that we interchange the order in which these three-dimensional functions appear. And with such identities that are the one given in the previous slide, we can basically look to obtain some type of system of Poisson brackets which are related to the following system of expressions, namely the fact that, again, like I've been describing for the viewers, the fact that we would like to be able to deduce that some type of integrable and exactly solvable structure holds for the Poisson from the Poisson structure of the inhomogeneous six-vertex model, which we can basically reparameterize with computations from the L operator and how that would relate to Poisson structure and integrability and exact solvability, tentatively speaking, for the 20-vertex model under domain boundary conditions, given the insights like I'd mentioned from Di Francesco and related types of works from basically the determinantal representation of the partition function. So basically, given these two types of equalities that we've been describing, I also wanted to just very briefly present for the viewer what is the expression in terms of this R factor, this three-dimensional function, which is appearing in terms of these two terms and these two components, which are appearing in these two Poisson brackets of, or in which in these these two tensor products of these Poisson brackets of transfer matrices, which is just basically given by the fact that we can have R plus being identically equal to the limit as y tends to positive infinity of some function e, which I'm not really going to explicitly define it, except the fact that it's just basically being a function of spectral parameters, as well as having a tensor product of this representation with e multiplied by some little of r term, as well as similarly for r minus, which is given by identically equal as limit as y tends to minus infinity of a very similarly defined quantity. And so additionally, these three-dimensional R terms, which I provided some type of expression for the viewer for in the previous slide of the presentation, which are relating to computations with the Poisson bracket that we would like to perform on the previous slide, they can also be used to study a tensor product of the following four, namely a tensor product of these two finite dimensional representations of transfer matrices, namely this R plus term times one representation of the transfer matrix, which is entering into a tensor product with another transfer matrix minus as some type of other manifestation of some type of anti-commutation relation with transfer matrices, just basically minus this three-dimensional representation of the transfer matrix, which is entering in terms of a tensor product with the transfer matrix multiplied by the three-dimensional function as y tends to minus infinity, or as the spectral parameter, or as the spatial parameter tends to minus infinity, instead of to plus infinity, which is given as the first term of this tensor product. And so ultimately, in three dimensions, the existence of the action angle coordinates for a three-dimensional Hamiltonian flow would imply that, again, the action angle coordinates, which are a function of the spectral parameter with respect to its complex conjugate, would vanish. And as in the two-dimensional case for the inhomogeneous Hamiltonian flow for the six-vertex model, the fact that that there is integrability of the limit shapes of this model implies that the action angle coordinates phi, which are a function of the spectral parameter lambda, with respect to the complex conjugate of psi, are also identically equal to zero and identically vanish. And in three dimensions, as we've been describing, to just basically juxtapose how computations and staggering and spectral parameters can be defined over either two dimensions in Z2 or either over three dimensions in the triangular lattice, are relating to, again, the large N asymptotic limit of these transfer matrices, which would include the following terms, namely the fact that, again, one would recall that these are representations of L operators, which were introduced in a 2010 reference that I described, which was titled Exercises with the Universal R Matrix, which is pretty much relating to Booz and colleagues, and pretty much how this relates to just basically introducing different types of schemes or different types of ways for defining spectral parameters over the triangular lattice, and how these products of L operators and these operator representations that one would be able to obtain from L operators and L matrices would be able to deduce that some type of suitable action angle coordinates exist. And this is basically given by the expression that's given on this slide, in that we're looking at some large N asymptotic limit, namely we're taking a product of some L operators and we're varying the spectral parameters about 1 degree of freedom. Namely, we can see that these Q terms, which are relating to parameters which are introduced as tensor products over two quantum groups, is being introduced in terms of just basically varying the spectral parameters about 1 degree of freedom of the triangular lattice. And then for the remaining terms, in this type of asymptotic expression of L operators, which is being related to the transfer matrix and to the traits of the transfer matrix through the quantum monodromy matrix, is then being obtained by just basically varying all of the spectral parameters, which are given by entries of these L operators, which are constructed from oscillatory algebras in root systems. And just basically these oscillatory algebras and root systems, I'll be able to scratch some of the surface from this, obviously, in this presentation, because it's a very complicated type of basically computations and structure for these operators that are being able to obtain, and how this is pretty much being related to the Dynkin automorphism of, or the automorphism action of the Dynkin diagram, which is just basically relating to the symmetric group, in which you're basically trying to permute different types of entries of these L operators to be able to actually obtain a broader family of L operators, which would then hence theoretically be related to some type of generalization of the Poisson structure and with computations with the Poisson bracket that I've been describing and motivating for the viewer in this presentation. And further developing on this perspective exhibits clear similarities and, on the other hand, also differences with computations with the Poisson bracket in two dimensions, because we have been describing how the Poisson bracket, being a function of two spectral parameters, lambda alpha and nu k, for this L operator, which is introduced in a reference due to Colombo and Pronko, is given by the finite dimensional representation of, namely, sine of lambda alpha minus nu k plus eta up sigma z of k, which is just basically one of the polybasis elements which I'd introduced previously, namely those group of traceless 2x2 matrices, as well as being also proportional to the sine of 2 eta term, which is multiplied by another polybasis element, as well as another term on the antidiagonal for this two-dimensional representation, namely sine of 2 eta of sigma k plus of k, namely another polybasis element. And finally, for the last term in this L operator, in this finite dimensional representation for the L operator, sine of lambda alpha minus nu k minus eta a sigma z of k. And this is, again, all relating to this type of finite dimensional representation for the monodromy matrix, namely the collection of operators A of lambda of alpha, B of lambda of alpha, C of lambda of alpha, and D of lambda of alpha, which are all being related to the spectral parameters lambda of alpha, which are ultimately first introduced from the staggering of this vertex model, or the presence of inhomogeneities over the square lattice from this L operator, which is first introduced under domain wall boundary conditions. And this is to say that for approximations of the three-dimensional transfer matrix, namely, if we're looking again at L operators for the 20 vertex model, which is given in terms of some product over I and J terms, where these I and J terms are corresponding to the specific positions and sites of the triangular lattice for the 20 vertex model, we can now turn a system of the Poisson brackets to approximate in the large n asymptotic limit from, again, the system and the collection of 16 Poisson brackets, which I've been describing and motivating for the viewer in earlier slides of this series, and how this relates to the inhomogeneous Hamiltonian flow and the integrability of this Hamiltonian flow for the 6 vertex model, and even conversely, or ultimately, how this relates to integrability of limit shapes and action angle coordinates for the 6 vertex model. So this is pretty much a way to look at and to connect all these types of vertex models together through the existence of suitable action angle coordinates, and as well as integrable and exactly solvable structures. And so pretty much in previous works of the author and me, integrability of the 6 vertex model was established with several computations with the Poisson bracket, namely the fact that if we look at two test functions f and g, we can look at, again, this type of representation being identically equal to the integral over some finite volume instead of just over the entire real line, of just basically these difference of two partial derivatives with respect to either the solution tape psi or the complex conjugate of psi of the nonlinear Schrodinger's equation, as well as also the tensor product of the Poisson bracket, namely given by the fact that we instead look at two test functions a and b, and we replace the standard multiplication from each one of these partial derivatives with the tensor product from these two differences of partial derivatives that we're looking at, that we're integrating with respect to the standard Lebesgue measure. And I also wanted to take some time to introduce the 4 vertex model, because I've been describing how the 4 vertex model, the 6 vertex model, and the 20 vertex model can be used to establish various types of connections with the 11 vertex model. And this is due to a 2007 work due to Bogolyubov, in which he describes several types of connections with the 4 vertex model and box plane partitions, as well as several combinatorial type of related problems. And this is given by the fact that the 4 vertex model under fixed boundary condition C supported over the square lattice Z2, the probability of sampling some configuration omega is identically equal to the weight function of the 4 vertex model related to which is a function of omega, the configuration in the sample space normalized by the partition function so that this expression is a probability measure. And this is overall relating to the fact that the explicit expression like we've given for the four vertex model is a lot simpler in comparison to the expression from all of the six type of combinatorial possibilities, which are introduced for the weight function of the 20 vertex model, because it's pretty much given by the types of configurations which are given by the six vertex model by excluding the configurations from the isotropic parameter B. So this is just basically explicitly given by the fact that it's A of n1 plus n2 as well as C of n5 plus n6, excluding the configurations assigned to the isotropic parameter B. And again, in this 2007 work due to Bogoliubov, he introduces a type of expression for the partition function, which is included, which is appearing as a normalization factor in the probability measure in terms of identically being equal to a sum over configurations little omega beginning to the sample space big omega of the four vertex model, as well as just basically given as a product of weights between minus n between k up to -1 of just basically these three possible weights, which are given by just basically being indexed in terms of specific positions of which we're basically assigning configurations of the four vertex model over Z2, namely the square lattice, as well as the remaining term, which is given in terms of the summation over configurations as a product over little j of these three similarly defined weight terms, which are even given in terms of being proportional to the weights A, B, or C. Unfortunately for us, this is really making apparent why we were talking about and discussing the whole time integrability and exact solvability, and how this relates to action angle coordinates and solution to the KdV and the NLS, the nonlinear Schrodinger's equation, because Bogoliubov, in his 2007 work, he describes a very convenient finite dimensional representation for the L operator, which again can be used and leveraged within this work that we've been describing since the beginning of the presentation and making remarks about in terms of the Hamiltonian method in the theory of solitons from that seminal work, because we can be able to build some type of representation of the transfer and quantum monodromy matrices from products of the L operators, in which specifically for the four vertex model, we're again denoting U as some type of spectral parameter over the square lattice for this model, and little n as some strictly positive parameter, which can be identically decomposed in terms of the representation of L1 of 1, L2 of 1, L1 of 2, and L2 of 2 in terms of minus U of E of n, sigma minus n, which again is a polybasis element, as well as sigma plus, which is a remaining polybasis element, and the reciprocal of the spectral parameter times E of n, where these E of n terms, which are appearing upon the diagonal of this 2 by 2 finite dimensional representation for the transfer matrix, are given in terms of the basis elements, just 1 of 0 and 0 of 1 of the square of Z2. Inequalities for the transfer matrix, which we have presented earlier for the 6 vertex and 20 vertex models, relate to just basically equalities of the transfer matrix in the 4 vertex model. Just basically, we can look at the tensor product of the Poisson bracket of the asymptotic representation as the spatial parameter tends to minus infinity or to positive infinity by making use of a very similar set of equalities, which was given as what was provided in the 20 vertex model, just given by the fact that we have to define these little r terms differently, as well as the transfer matrix is defined differently for the four vertex model because it's after all being related to and being defined in terms of some type of asymptotic expansion and product of L operators, which was defined by Bogoliubov in his 2007 work in the previous slide. And these types of equalities can again just be related to, again, these three-dimensional functions which were defined for the 20 vertex model, as well as the type of three-dimensional representation of the transfer matrix, which is again relating to the construction of the universal R matrix, and as well as again to oscillatory algebras and root systems in tensor products of quantum groups. And so altogether, the Poisson structure of the four vertex model is a particularly good one to look at because it's a little bit simpler than some of the other types of Poisson structures in the computations with the Poisson bracket for the 6 vertex model, the 20 vertex model, and even for the 11 vertex model. But altogether, this is just given by the fact that the script I of terms, which are given as finite dimensional representations for the operators, which are appearing in block representations of the transfer matrix, can approximately be speaking asymptotically approximated by just the reciprocal of u minus u prime. And this type of approximation that I've given in the first term, which is appearing in C of 1, is appearing for all other terms which are appearing from operators from the transfer and quantum monodromy matrices when we're just basically taking products of L operators, as long as the arguments in each one of the Poisson brackets are the same operator, but we're just changing the spectral parameters. So this is really something that's a great type of idea or intuition to have in mind, because when we're basically looking at other types of ways in which we can approximate and make the most use of different types of structures of operators for being able to perform these computations with the Poisson bracket, it's pretty much really helpful when we can have some type of simple approximation, maybe for finitely many Poisson brackets within the entire Poisson structure, and how then we can turn our attention to the more non-trivial brackets or the more non-trivial Poisson brackets that would actually need some type of combination of these properties of the Poisson bracket, which are relating to anti-commutativity, the bilinearity rule, the Leibniz rule, which are the three main properties out of the four properties which we're using when we're performing computations with the Poisson bracket. And the Poisson structure for the higher spin XXX chain, which is another type of quantum spin chain, can be inferred from that of the four vertex model. The fact that if we're looking at the support of the first operator, A of U, all the way up to the support of the fourth operator in this finite dimensional representation for the transfer and quantum monodromy matrices, it can be identically expressed in terms of a span, namely the set of all linear combinations of the A operator, or the first column or representation in the transfer and quantum monodromy matrices, all the way up to the D term, or the fourth operator. And this is basically given by the fact that, again, the L operator for the higher span XXX chain, it's defined in a very similar type of way, except we're denoting lambda instead of U as a spectral parameter, and we're denoting little n as some strictly positive parameter that's denoting the size or the magnitude of the finite volume for the higher spin XXX chain, and how this is defined in an extremely similar way, just in terms of projectors, and how this is relating to the Pauli basis elements, and overall how by taking products of these L operators, we can obtain some type of finite dimensional representation for the higher spin XXX chain transfer matrix. In similar methods by which one can introduce notions of solvability and action angle variables for the Kamasa-Holm PDE relate to computations with the Poisson bracket for the inhomogeneous six-vertex model, which is to say that due to these two authors, Konstantin and Ivanov, they even discuss and talk about Poisson bracket and action angle variables for the Kamasa-Holm equation, which is pretty much demonstrating how much of a robust framework this quantum inverse scattering method is providing for in terms of being able to perform some types of computations with Poisson brackets for this highly non-trivial partial differential equation. And this partial differential equation is also describing wave propagation phenomena in a similar type of way that the KdV equation is, but its nonlinearity is different in the fact that, as you can see, this U of XXX term, namely the third partial derivative of the solution U to some well-posed under some well-posed initial condition for the Kamasa-Holm PDE, is also being accompanied by a product of U of X, namely the partial derivative of U term with the second partial derivative of the solution U of XX term, as well as several other types of factors, which are overall constituting a more complicated set of nonlinearities for this partial differential equation of interest. And again, this is to say that we're trying to draw and establish connections between integrability and exact solvability, which is again drawing our attention back to the inhomogeneous six-vertex model reference due to Keating, Reshetiko, and Sridhar, in which they establish and conjecture that integrability of the inhomogeneous Hamiltonian flow for the six-vertex model should hold as a result from integrability of limit shapes, from just basically choosing a suitable L operator, being able to perform computations with this L operator and relating it to computations with the Poisson bracket, as well as even determining whether there's some type of analog of this argument from the six-vertex model to the 20-vertex model to the four-vertex model. And like I've been describing briefly, for the present throughout the presentation for the viewer how this relates to the 11 vertex model, a more esoteric model, vertex model, a statistical physics, which has connections to polymers. And this is just basically to say that another type of way which we can basically try to reformulate a task of interest with regards to the L operators which are provided in the computations from the reference of exercises with the universal R matrix by Booz and colleagues is that we can look at the following decomposition for the L operators which are given in 3 dimensions and how we can provide some more types of observations with regards to how this relates to oscillatory algebras, root systems, and again, tensor products of quantum groups, and how this relates to integrability. And this is basically given by the fact that this C term, which is appearing in the second entry in the first column of this finite dimensional representation for the transfer matrix, is given by a mapping into a unital associative algebra, as well as a term that's appearing in the first column in the first entry of the first column of this finite dimensional representation of the L operator, which is given in terms of a tensor product of differential operators, as well as remaining very similarly closely related terms, which are motivated the the construction of a tensor product of two spaces, namely two quantum groups, which are basically used to just basically basically denote transfer probabilities for the system amongst different regions of the triangular lattice, or more generally of the underlying lattice, depending upon whatever vertex model you're interested in considering. And basically, all of these terms are related again to, very generally speaking, to the Dynkin automorphism action of the automorphism action of the Dynkin diagram, because you can pretty much introduce this automorphism action to basically interchange certain columns and certain operator representations in this 3-dimensional representation to in fact obtain a family of L operators, in fact 6 L operators, which is corresponding to the cardinality of S3, namely the fact that there are 6 transpositions or 6 ways that you can basically exchange operations in the symmetric group with 3 letters, and how this is relating again to the Dynkin automorphism and the underlying Dynkin diagram. And this is overall allowing us to establish a lot of types of connections between integrability and exact solvability, because this is really in some ways relating to the Ising model, because the Ising model is relating to the 6 model and to the 6 vertex model and other types of vertex models in the Gaussian free field, because it's demonstrating connections with several other types of models, because pretty much the Ising model and the Potts models, they're very prototypical type of models in statistical mechanics that were first described in even in my work, even just in my work, which is obviously a small portion of the entire literature within the field, I really started out looking more in terms of normalization of crossing probabilities in the dilute Potts model, looking at adaptations of the Seminole-Powers argument for demonstrating that phase transition occurs for the long-range Ising model, or even looking at correlation length lower bounds for the random field Potts model, or even looking at discretely holomorphic parafermions and parafermionic observables for vertex models, and which has connections to fermionic observables for the abelian sample, and how this can even be related to logarithmic delocalization of the height function of the 6 vertex model, and how later in more of these recent works, which I've been describing for the viewer, how this relates to integrability and exact solvability, and even the D23 spin chain, which I'm going to be updating on the archive soon. And we can think about making a transfer, like making or basically establishing a bridge like we've been describing from the quantum monodromy matrix to the transfer matrix, because basically how we had described in terms of the weights for the 6 vertex model being introduced in terms of being a function of 2 external fields, namely an electric field and a magnetic field, which are typically denoted with H and V. These 2 spectral parameters, U and as well as a collection of spectral parameters V sub k, can be used to define the quantum monodromy matrix in terms of, again, the trace of the transfer matrix given by the fact that the magnetic field is set to be to 0, this component is set to vanish, as well as also being a product of diagonal matrices, which are acting as a prefactor in terms of the trace of the transfer matrix to define the quantum monodromy matrix, which is related to the explicit expression which is used for deducing that integrability of the inhomogeneous limit shapes holds from integrability of the or basically can imply integrability of the Hamiltonian flow for the six vertex model in the presence of inhomogeneities. And this is again relating to the fact that I described earlier in the presentation for the viewer that there are a lot of connections and intricate dependencies of the boundary conditions, just in the same way that basically there maybe could not exist a certain type of solution or desirable analytical solution to some type of partial differential equation, depending upon what type of behavior you enforce to the ansatz of the solution at the beginning of the time evolution. And this is pretty much very much the same type of case in a discrete sense when you're looking at the six vertex model, because basically in one of my preprints, which is currently submitted and under peer review right now, I discussed just basically ways to formulate crossing probability estimates for the Ashkin-Teller model and for other types of spin models, and how that relates to just basically frozen boundary conditions, and pretty much in which pretty much you're introducing defects in which just basically groups of vertices for the six vertex model can be frozen simultaneously, and how this relates to seminal arguments provided by Dumino-Copin, Manulescu, and Carilla and Ulamara, in which they pretty much describe how to just basically formulate crossing probability estimates to hence conclude that logarithmic delocalization of the height function holds when you're basically looking at sufficiently flat boundary conditions. And this pretty much relates to the sample space which I'm providing in the uppermost right-hand corner of this slide, because this is demonstrating how one can establish just basically various types of generalizations of configurations of sample spaces of configurations for higher spin chains like the D23 spin chain that I've been mentioning at various points towards this presentation of the series, and how this results to an image which I took from one of Dumino-Copin's work with his colleagues, in which they reproduced the conjectured phase diagram for the six vertex model, in which pretty much the phase diagram is consisting of just basically boundaries which are given by this disorder parameter, which is delta is equal to a squared plus b squared minus c squared normalized by 2ab. And basically, depending upon whether this parameter is equal, this disorder parameter for the six vertex model is equal to plus or minus 1, you can basically encounter ferroelectric or anti-ferroelectric behaviors in the system, and how this is pretty much determining whether certain types of integrable or exactly solvable properties would be expected to hold depending upon the boundary conditions and the disorder that's present in the system, and how overall this is relating to quantum spin chains and beta ansatz and so many related topics which we've been discussing. But this is really related to the fact that the limit from the previous slide is related to studying the following two asymptotic limits. So basically, in the same way which we have been describing and motivating several types of topics in which we're looking at just basically asymptotic limits of the transfer matrices and the quantum monodromy matrices, for the 20 vertex model, given the construction of the universal R matrix, we can just basically look at a representative for just basically the transfer matrix over a weak finite volume limit by just basically taking a product over little I and a product over little j, and sending little m to positive infinity and little n to positive infinity, and looking at just basically the product of these representations, just basically 1 of I of j all the way up to 9 of I of j, and how this just basically simultaneously results to looking at the limit as n tends to positive infinity of just 1 of I of j up to 9 of I, or 1 of I up to 9 of I, as well as also the limit as big N tends to positive infinity as 1 of j up to 9 of j. And this is all relating to the fact that we're being described that integrability under a certain class of boundary conditions for triangular eyes, namely the 20 vertex model, would fail to hold due to the lack of an analog for the following property of action angle coordinates for the inhomogeneous six vertex model, which again is just basically saying that action angle coordinates, again from the seminal reference due to Vadev and Takatan in their seminal work Hamiltonian methods in the theory of solitons, is relating to the fact that we're looking at just basically the action angle coordinates of phi of lambda, the spectral parameter, with the convex conjugate of this quantity being identically equal to 0, where this phi term is given by a square root of the density times the exponential of this minus I of phi term, where again this phi term, which is appearing in the power of the exponential, is given in terms of some type of asymptotic quantity, which appears in terms of the behavior of the solutions to the nonlinear Schrodinger's equation, where this phi of lambda term, which is appearing as the square root of the density term, is given by 1 over 2 pi psi, namely some type of quantity or some type of prefactor, which is reciprocal to 1 over the magnitude of the nonlinearity term, or the prefactor for the nonlinearity, which is appearing in the nonlinear Schrödinger's equation of the natural logarithm of 1 plus epsilon, namely this should be I think this should be chi. I'm sorry for the small typo, but it should be proportional to the square, or the operator which is appearing in the uppermost right-hand corner of the finite dimensional representation for the transfer matrix of the six vertex model in the presence of inhomogeneities. And where again now we're seeing that this phi of lambda term, which is again appearing in the asymptotic behavior of the solutions to the nonlinear Schrödinger's equation, is minus the argument of the second operator, that same operator which is given in the uppermost right-hand corner of the finite dimensional representation for the transfer matrix. So this is just really providing an asymptotic expression and demonstrating how the behavior of the asymptotic coordinates it relates very much to the asymptotic behavior of the solutions to the nonlinear Schrödinger's equation, which again is ultimately related to well-posedness, as well as in a discrete sense being related to domain boundary conditions or to fixed boundary conditions in the case of the four-vertex model. In DiFrancesco's determinantal representation for the partition function, it's really a great type of expression to have, so I just wanted to include it later on in the presentation in this series, which is pretty much being related to the fact that it's a determinantal representation of these types of combinatorial factors, which is being related to domino tilings of the Aztec diamond. So just pretty much in the same type of way, like I mentioned for the view that the four-vertex model has expressions in relations to combinatorial properties and box plane partitions, the determinantal representation of the 20-vertex model, it's being related to tilings of the Aztec diamond, which is some three-dimensional which is encapsulating various three-dimensional types of combinatorial aspects. And these U and V terms are given by the spectral parameters, which are given over the triangular lattice, as well as the fact that this little n of term is denoting some aspects of the size ratio of the finite volume over the triangular lattice. And basically how we're looking at just basically this 1 plus little u of squared terms, as well as the remaining term in the numerator of this determinantal representation being related to 1 plus 2 of u minus u squared, as well as the denominator having mixed contributions, or basically contributions from u and v simultaneously. And it shouldn't come as a surprise that we've been talking about the Poisson bracket of the tensor product for transfer matrices for the four-vertex model and how it relates to the six-vertex model, and just pretty much how this can be explicitly related in terms of just the Poisson bracket of the tensor product from these two transfer matrices, where the first transfer matrix and the first argument of a Poisson bracket is given by u, and the second one is given by u prime. And just basically these types of Poisson brackets, tensor products of Poisson brackets between these two transfer matrices are very much underlying and constituting the type of Poisson structure which we'd hope to be able to analyze for the 20-vertex model, because pretty much we're seeing how we compare from the first argument one entry same, say A of u with A of u prime, A of u with B of u prime, and so on and so forth, which is constituting the total number of terms within this entire Poisson structure, which is relating to the Poisson structure for the six-vertex model in the presence of inhomogeneities. And for the 20-vertex model, it's a little bit different because we have to keep in mind, for the purposes of the quantum inverse scattering method, that there are these three standard bases for the triangular lattice, namely the up basis element is given by square root of 3 over 2, 1/2, and 0. The side basis element for the triangular lattice is given by square root of 3 over 2 minus 1/2 and 0, whereas the last basis element of the triangular lattice is given by 0, 0, and 1. And this determinantal representation of the transfer matrix and also, of the partition function due to DiFrancesco, it's relating to U-term boundary conditions. So counterintuitively, actually, or maybe not so counterintuitively, maybe one could expect that domain wall boundary conditions for the 20-vertex model can be related just basically to endowing some extra structure, some additional structure through U-term boundary conditions for the 6-vertex model, and how that relates to determinantal representations of the partition function, which can even be leveraged and used for obtaining contour integral representations under domain wall boundary conditions for the 20 vertex model from the 6 vertex model. And this is basically given by the fact that the determinantal representation for the partition function of the 6 vertex model under U-term boundary conditions in the presence of inhomogeneities is proportional to some determinant of script m prime, where m prime is being related to just the reciprocal of some function of the weights a and b, as well as minus another term of the reciprocal of some other function of the weights a and b, where these again are relating to the isotropic parameters, which can be introduced for the probability measure of the 6 vertex model and the 20 vertex model alike. And the three-dimensional Yang-Baxter algebra is coming into play because it's just basically saying that the set of relations and set of commutation relations, which we can expect when basically multiplying operators together for transfer matrices and quantum monodromy matrices of the 20 vertex model, is related to the three matrices. We can basically see this matrix that's given on the rightmost side of the slide is given as a function of u, and then the middle is u prime prime, as well as the final last spectral parameter u prime. And this is just basically some of the relations which are given by just basically multiplying operator representations and finite dimensional representations of the transfer matrix, which is constituting the underlying Yang-Baxter algebra. Namely, we're looking at, say, A of u and A of u prime and A of u prime prime, as well as D of u, and D of u prime prime, and how this is relating to several types of relations and commutation relations and product and expressions for products of these operators, which one would hope to be able to deduce from the transfer matrix. And I just wanted to close out this presentation of this series by describing a few more esoteric models and how this is again relating to pretty much the 11 vertex model, which is almost like a hop, skip, and a jump away from what we've been describing in terms of the 4 vertex model, the 6 vertex model, and the 20 vertex model. And this is relating to the fact that solid on solid models are very much related to the 7 vertex model and other types of models, because you can look at forming Boltzmann weights, which are some of the underlying weight parameters and weight functions which are introduced for these types of models, and how it relates to fusion procedures. So basically, a fusion procedure is related to, like how we have been describing, solutions to the Yang-Baxter equation, but actually being able to augment and being able to increase the total size of the solution set of this equation from some initial statement of an R matrix. And this is again just the reference, just providing explicitly the reference for the universal factorization of the universal R matrix factorization for the 20 vertex model through this 2010 reference, which is very much an indispensable reference for being able to deduce some type of existence or statement of action coordinates, Poisson structure, and Poisson brackets. And then finally, this is some of my previous work from 2024 that I'm going to be updating soon, maybe in a couple of months, as I've been working on some things in which, like I've been describing for the viewer, I've been looking at quantum inverse scattering for the 20 vertex model up to this action of the Dynkin automorphism, namely up to the automorphism action of the Dynkin diagram, and how this can relate to Poisson structure, triangular height functions, and determining some weakening of integrability from the existence of action angle coordinates that may not necessarily have a vanishing Poisson bracket. And this is just all to say that the universal R matrix, which I have been describing, has this type of factorization, namely, given some strictly positive parameter delta, which is appearing in terms of this R matrix, we're introducing a product of 3 universal R matrices, namely one that's depending upon a scale less than or equal to delta, one that's of a scale approximately the same as delta, and one that's greater than or equal to delta, multiplied by an R matrix, by a K matrix, where this K matrix is determined as an exponential of a Planck's constant. And I felt that this type of expression was something that's really great to have more near terms, more so near the end of this presentation, because it's pretty much relating to a lot of the fundamental constants of nature, the Planck's constant, which is ultimately relating to quantum mechanics and quantum physics and the Heisenberg uncertainty principle, and how this is relating to a lot of the types of computations with the Poisson bracket, which are going to be coming up from an upcoming presentation or an upcoming paper on the 11 vertex model, which I hope to have on the archive soon. And this is to say that explicitly, we have been describing from this expression, from this reference of the exercises with the universal R matrix, that there are several types of expressions, namely the fact that, again, like I just described for the viewer, this K matrix is given by an exponential of a Planck's constant times a summation over these two basis elements from corresponding to the two for the roots over the quantum group, over the tensor product of the quantum groups, as well as these other R terms, which are given by, again, just tensor products of these elements over these two of these roots over these quantum groups, and how that relates to oscillatory algebras and the root system, which is given by this delta term, delta plus a minus of A, which is pretty much determining how all these types of expressions can come into play in terms of the universal R matrix factorization, as well as integrability and being able to perform very specific types of computations with a Poisson bracket. And the intertwining relation, like we have been describing, is allowing us to relate, say, for one instance, the 7-vertex model, which is another more esoteric vertex model of statistical physics that I didn't necessarily describe or define formally, but I was just describing, and how this relates to an intertwining relation, namely the fact that if we start at the R matrix with an R matrix and we multiply it by a tensor product of two intertwining vectors, it's given by an intertwining relation because we're able to basically reverse the orientation in which these two tensor product of these two intertwining vectors appear in this expression, multiplied by the Boltzmann weight matrix W. And again, this is just demonstrating how a lot of these types of ideas and associations which we're trying to determine and being hopeful or optimistic that we can establish in integrable probability in statistical physics is pretty much relating to the fact that a lot of these types of objects for many types of models are related to each other by performing very specific and targeted transformations, such as this intertwining relation for being able to transform an R matrix of a vertex model into a Boltzmann weight matrix of a solid on solid model. And so I wanted to end up with some concluding remarks is that we were describing and motivating connections between the 4-vertex, 6-vertex, 11-vertex, and 20-vertex models, and to describe some connections from my previous works. We formulated transfer matrices, quantum monodromy matrices, as well as product L expansions. And as emphasized throughout several parts of this presentation, such computations are extremely dependent upon boundary conditions. And for the most part, boundary conditions for vertex models in previous works are shown to be integrable and exactly solvable under domain walls, namely under domain wall boundary conditions. But for the 4-vertex model, there were fixed boundary conditions. And altogether, a great type of perspective to have in closing out this presentation is that determining whether other classes of boundary conditions imply integrable and exactly solvable structures is of great interest to further explore or in the future. And thanks for watching.